Okay, so this week we are on Module 10. We're already on Module 10, so really getting there here, guys. Module 10, we get to do data exploratory analysis in data science. Now, we did a little bit of this earlier in the semester, but this week I want to give you a few more tools that are quite useful in trying to first have a look at the data, and second, to transform it in a way that it is better for doing your analyses or your model. So this week is a little different, maybe not hugely different, but I have just one assignment this week. It's a larger assignment, and I will ask you to essentially do these things that I'm explaining to you on a data set. So each one of these things you'll want to be able to replicate for the assignment this week. So first topic in this week's module is just called data shape. Data shaping is kind of a statistical analysis of the data, just to get, again, a better feel for it, so we know what to do with it. Like I said, we've done a bit of this already early in the semester, but not a lot. This week, I'm going to give you some tools that you can use. The first one I want to show you is called box and whisker plots. And these can be really useful, again, for a quick look to get information about your data without having to dig too deep, just by one simple visual. With a lot of data packed into it, you'll see here in a second, you can get an idea of each of the attributes in your data set, at least the numerical ones in this case. So here on the left, I'm showing an example of a box and whisker plot that just kind of labels out the different components of it. So this is what it looks like. And you can see this center part here, I guess, looks kind of like a battery. And then you've got, these are called your whiskers. This is your box in the middle. These are clear whiskers coming out. And what this does is it shows you for one of your attributes. So if you have a numerical attribute that goes across a range of numbers, right, as they often do, it gives you an idea of where the data lies within the range. So end of the whiskers, the minimum and the maximum are essentially the lowest numerical data point and the highest numerical data point in that attribute range. And then the bottom of the box is what's called the first quartile, which essentially means the 25th percentile of the data. That means 25% of the data set for the data attributes numbers are smaller than that point, and 75% of them are bigger. And then the next one, always put inside the box, is the median. And remember, the median is considered the middle data point in the data set. I want to make sure we don't get that mixed up with mean. Mean is the average. Median is the middle data point in the data set. And then the third quartile is where you would hit the 75 percentile point in the data set. The box essentially encompasses from 25% up to 75% of the data. And then the upper whisker on the plot goes to the 100th percentile, essentially the highest data point in the data set. And just looking at this, you can see a lot of information about the data. Just kind of trying to show you how this would map to a distribution. This one here, this first one, these two go together, top to bottom. This one's called left skewed, and you can see that it has a long tail. So this always bothers me because I always feel like it should be right skewed because it looks to me like it's leaning to the right, but it's actually left skewed because the long tail is on the left. So this data set is left skewed. And when you put that into a box and whisker, you can see the left side is longer, and the 25% to 75% range is pushed over to the right, because the majority of the data points are on the right side of that distribution, even though it's called left skewed. A symmetric one, the box would be perfect in the middle, and then your whiskers would essentially be the same on both sides, and then right would be obviously the opposite of that, where they lean. The tail is on the right, right skewed, and the majority of the data points are on the left side. Also here, it's not really labeled, but you can see that this one, the box itself is smaller, and that tells you that the data points in the central range are more compacted together, because that 25% to 75% are fairly close together. And then the whiskers on this one look a little long, which tells you that it has more of a longer tail or longer outliers on the outside of that range. So they're just quick ways to look at these things and be able to pull a lot of information from this simple visual quickly. I think I have another, no, I don't have another one there. So I'm going to just hop over to Orange and show you how to do this real quick. It's super easy. We'll be going back and forth again like I've done previously to show you how to use the tools some more. I'm going to try this and hopefully my internet cooperates today. I've got a whole bunch of stuff in here, of course, because I've been messing around quite a bit. But you can see the two data sets we're going to work with this time around are at the abalone one again, which is that snails, the different attributes of snails. And then, of course, I'm going to have to do iris a little bit. Just need to wait iris. But the first part here with abalone, you can see all I did was I just attached the box plot object to the output of abalone. Abalone, really figure out how to say it. And when I open that up, you can see it throws a box plot in here. Of course, it's on the side, not up and down. But it essentially needs the same thing, or entirely needs the same thing. You can see I've got the whiskers here coming out one end and the other. I've got my 25th percentile, shows here it's 0.45 for length. The median is 0.545, and the 75th percentile is 0.615. So it gives me a good idea of how this data is distributed just by looking at this. Again, it's kind of nice and orange. I can just click through these different things and I can see how the box plot looks for these. So if I wanted to look at diameter, I can just click on that and it'll immediately give me the box plot. Height is obviously very tightly packed together, which tells me that there is a very short range the vast majority of abalones have for height. And there's some very unusual, apparently, outliers that are, it may even be just a single data point that takes it way out here. Hopefully that's coming through, that line's kind of thin, but it goes all the way out here to 1.15. So each one of these I can quickly see some information about it. The other thing that I like here is that I can actually utilize my target. So the target variable here is sex. There are actually three values in this data set for it. There's male, female, and infant, which is just I. So they designate that separately. The I does the data, and later on I pull it out because it's kind of hard to. So I can add a subgroup here of my target variable, and you can see that it breaks it out into different boxes layered on top of each other based on what based on how that value would be. I'm not going to say this correctly. It essentially breaks it out by the different categories. So females have this distribution, males have this distribution, and infants have this distribution. So it allows me to use a categorical variable. So it allows, sorry about that, kids keep trying to run in here and getting in my way. So you can see here I've got those split out based on categorical variables, so I can see how a categorical variable affects the different distributions. Kind of a nice thing to be able to do. Again, to take a quick look at the different data points put out that way. So that's box.
Hey, Matthew?
Yeah.
So in this example, where since you're sharing your screen, so like that top number, 0.27 to 0.326, give or take, would that be the first quartile? And then like 0.326 to 0.335 would be the second quartile, and
so
like 0.335 to 0.390 would be the third.
Yeah, so this so from 0.270 to 0.335. This is from the 25th percentile to the 50th percentile.
Okay.
Because that's the median, that would take you to the mean, and then 326 to 390 would be from 50 percentile to 75th percentile.
So they're talking about the second and the third, and the first would be on the other end of one whisker, and then the fourth would be on the other end of the other whisker, right? That's
correct. Yeah.
Okay.
When they say the first quartile and the third quartile, it's a little bit misleading, but it's essentially where the first quartile ends.
Okay.
So it's sorry, that's a little bit misleading. Yeah, if you break it into four sections, first quartiles from 0 to 25%, and then 25 to 50, 50, 75, 75 to 100, obviously. So that's how that's distributed.
And what's that I 0.3206 plus or minus 0.0081? What's that?
Okay, I believe, I'm going to be wrong, but I believe that is the mean, but I don't know why there's a variation on it. So I might have to get back to you on that one.
Okay.
We're more concerned with the median, and the reason median's used over mean is because mean is more affected by outliers than median is. So a median generally with data gives you a better understanding of where the middle of the data set is than the mean. So I think that's mean, but I don't know why it has a variation. So let me get you that answer, and I'll have to drop an announcement or something because I don't have that.
And so the median here would be from those two middle whiskers, right?
Yeah. So
those two middle bars.
Yeah. So for infants, for ones that have a category of I for sex, it would be 0.335 is the median. For males, it would be 0.455, and for females, it would be 0.465.
I see. All right. Thank you. That's what I need to know. Sorry.
No, I'm glad you're asking the question. No, I prefer that to me just running through all this and not getting clarity for you guys. But I will get you the answer to that top part. I'll have to actually hit the docs myself and figure out why it has plus or minus there. So I will let you guys know that. Okay, so that's essentially box plots. So you can see it's quick. It didn't take me any amount of time to just attach it to my data set and just start digging through it to see some interesting information about the data and seeing where it's widely distributed versus tightly distributed with long tails. Those are the kind of things you want to look at. And then again, you can look at the skewing here. We'll also be looking at distributions here in a little bit where you can also see that skewing. But this is another way to be able to quickly see if something is heavily skewed one way or the other. Okay, so now I'm going to switch back over to my files. Okay, so the next thing I want to show you is histograms or distributions. So when you do a histogram, again, we're looking at the numerical data. What you essentially do is within that range again, you bucket the data points based on a range I'll show you, you can adjust on a range, and then count how many of the data points fall within each bucket from the lowest end of the distribution to the highest end of the distribution. And by doing this, you can quite well approximate the shape of that data. And so here's these are pulled from Orange, just from this thing I'm going to show you here in a minute. But you can see that I have created a distribution, and each one of these vertical lines is the counts within one of those buckets, from the lowest data point to the highest data point. And then I can estimate a distribution over the top of that. And you can see this one fits a regular normal distribution quite well, this particular data point. Obviously, other ones won't, but this one looks very normally distributed. And I'll show you again how to do that over here in Orange. So distributions next. So let me switch over. I really wish there was just a toggle I could use for this. Okay, so this time I've gone ahead and I've put a select rows object in here because the infant data set was really affecting how it looked for my distributions. So I took it out. So if I open up select rows, you can see here I just chose categorical variable sex is not I. So that essentially filters that out, so it doesn't get included in what I'm looking at after that, as long as I use the matching data to data line. You have to remember that if you just did data to data, then you're exactly doing nothing with your select rows because you're just passing the data through. You want to make sure you're using matching data to data to be able to utilize what you have filtered using select rows. Obviously, if you wanted to use unmatched data, you could also do that. In this case, I filtered out the one I didn't want, so I want to keep the remaining data or the matching data. Now if I open up this distributions object, I've already been messing around with this, so let me change this up a little bit. Okay, so this is how it normally looked the first time you load it up. And you can see that, again, I've got bins, and each one of my bins by default here is 1. You can see bin width 1, and then this is on rings. Apparently the minimum number of rings looks like 3, and the maximum number of rings looks like 28. And the way they figure this out is when they cut open the shell, they count the rings. So that's essentially what this count is on. And I can do this for each one of the items in here, so I can go through length, diameter, height, the whole works here, and I can see how the distribution looks for each one. Obviously, well, I shouldn't say obviously, commonly with things in nature, you will find normal distributions are very common. So I should not be surprised that each one of these things fits a common normal distribution. A couple of things I can do here. You can see this one, again, these bars look pretty wide. It has chosen a bin width of 0.1 for me. Sometimes you'll find if you have your bin width too wide or too skinny, it can actually affect the look of the shape, and it could also hide things that you might have a local minimum or maxima that get hidden because your bin width is too wide, or you might see like outlier groupings, like where you get too much in one group that looks like more of a spike if your bin widths are too skinny. So it's kind of a nice thing to be able to play around with a little bit, in which you can just do by dragging the bar around just to make sure you're not missing something with the bin width that's already set up. So if I take this one, this is shell weight, and I can just take this down, and all it's doing is, because I'm making the bin skinnier, I'm ending up with more bins. They won't be as tall, obviously, because there's more bins. But this one, if I take it down to 0.025, which is apparently the minimum it's going to let me do, you can see this is kind of a tall spike. It doesn't quite fit. I guess, well, see, this is what I was talking about. This feels like it might be a bit of an outlier here because it's affecting the whole distribution. If I take this up to a higher bin width, the whole thing is going to fit, presumably, a little bit better. Yeah, that's a tough one. But I guess the point is you could avoid, you could miss something if you don't pay attention to your bin width. If I have a bin width like this, I'm not doing a very good job of representing the data in my bins. It'll put the normal distribution look over it for you. That's what I'm trying to do. But obviously, you can see that in this case, it's not fitting the data because I've chosen a poor bin width. So that one's probably decent. Maybe here is decent too. It gives me an idea of how the data is distributed, and then I can overlay it with my nice normalized distribution. There's also several other ones here. I'm not really going to get into these, but you could look these up if you want to see what the different type of probabilities are. Each one acts a little bit differently. Obviously, that one looks significantly different, but that one wouldn't fit this data in any manner. But I've typically, with this data set, it fits very well with normal distribution. I can also hide the bars if I want. I don't like to do that, really, because now I'm not seeing my actual data points. You can, if you want it to look more visually appealing, I guess. And then I can do a split by. This actually, I'll be going into this in a little bit, so I'm going to leave that alone. But you can see that I can see distributions, and I can see it for all of my different items in my data set to see what it's where. Since it's very tightly grouped. Again, the bin width is probably part of the issue here. It still looks pretty decent. This one might have a local maximum and minima, the way this is distributed, or it might be the way that the data was taken. That's always something you have to take into consideration. The diameter is hard to bucket this tightly, so maybe there's some issues with the data itself. But again, I can affect the bin width just to see how that affects it. I think this one I would be cautious to say this is just normally distributed because it seems to have an issue right in that area. So that's just something you can do, again, to dig into the data and get a little bit more of an understanding about it.
Hey, Matthew, do you say that because it's leaning to the right?
Well, that's not necessarily what I'm, because you can still have a skewed normal distribution. That's okay. It's more the distribution itself is just trying to normalize across this data set, but this gap is pretty significant here, and then this bar stands up. So either what it could be is this bar is skewing how the normal distribution is trying to lay. Like I kind of wish I could just like remove some just to see how it would affect it, but I can't really. So either this just isn't a normally distributed data point, perhaps there's something about diameter that maybe if I split my female male, and this doesn't look great this way. Yeah, it's not going to tell me what I want to see. So if I were to split male female, I kind of wish I had a way to hide one or the other. So this might be part of it. So I've got male and female abalones in the same data. Maybe diameter is something that splits them, and you can almost, if you look at it, again, this is a visual thing, it's kind of hard to see. The males seem to, that higher data point might be because it's the maxima for the males, like the center of the normal distribution for the males, and then the higher one is the central distribution for the females. When you combine the two, you kind of get some weirdness. That could be related. Kind of hard to say. It's just something that I would be aware of if I'm using this data in a, it's probably okay because it's close, but in a modeling style where it expects it to be normally distributed, like a k-mean, for instance, a normal distribution. Cautious of data point. This series of data under the assumption that it's normally distributed. So I would keep that in my mind with me to like for cluster, a k-mean cluster. So it's something to keep in mind. Or I would have to dig at the data closer to see why I'm having that area in the middle where diameter isn't quite right. Presumably, if I'm doing data science around abalones in the real world, I'm probably some kind of a zoologist that knows a lot more about it than me sitting in my computer here. So maybe there's an explanation for that I'm not aware of. Again, I could dig deeper and see how the data was collected to see if there's some reason why that range is missing. I don't know. It's something that would require further digging to understand it. We don't have any zoologists in the classroom that know about abalones, do we? Or even how to say it. Okay, so yeah, that's what you would do with that piece of information. Okay, back to my presentation for 30 seconds here. Okay, so this slide's kind of nice just to give you an idea of what you might see with data shape when you do these kind of distributions. Symmetric, unimodal is essentially your normal distribution. You can see it goes up in the middle, comes down on the edges. Unimodal means that it has one peak, you know, right in the middle in this case. We talked about this. Skewed right means the data tails off to the left. The long tails on the right. See, I'm even messing that up. Long tails on the right. Skewed left is long tails on the left. And bimodal, this is where you kind of get those local maxima. Like you've got a bump on the lower end, and then it goes down, and then you've got a bump on the higher end again. So that would be bimodal. There's two high points from that data. Multimodal, with this amount of data, it's just a mess. You can see it's going up and down and up and down and up and down. Obviously, that would not fit a regular normal distribution. This might be a candidate for actually splitting the data in thirds to make 3 different data points, or try to figure out why you're getting peaks and valleys in it. And then symmetric is essentially, it doesn't matter where you are in the range. It just kind of is always the same. Take, for instance, if you rolled a die 500 times and 1 through 6 is the result, well, you're going to get the same across that entire spectrum, right? You're going to get the same amount of 1s as you do 2s, 3s, 4s, 5s, and 6s. That would be an example of something that would have symmetric distribution. So those are the kind of things you might see when you go to do these distribution visuals. Okay, so probability distributions takes that what we've already looked at, and it just kind of adjusts it in a way that you can see the probability of the data being anywhere along that distribution. Whew, that was not clearly said. So here I've got a visual, which always helps. You can see that this has been normalized in a way that the area under the curve, under the distribution, adds up to 1. It always adds up to 1 when you have these probability distributions. And you can grab a range, and within that range, you can say, like they've done here, you grab from here to here, it says 8.7% of this distribution falls from here to here. So, you know, if you were to put a line here, let's say right in the middle, again, let's say it's right in the middle of the normal distribution, 50% of it would fall below that line, 50% would fall above that line. It's very much the same as what we've already done, but you can talk about it in the context of probability, because you're normalizing it to be 1 for the area underneath the curve. I have not found a good way to do this particular thing in orange, unfortunately. So I'm not able to demonstrate this. I'm sure there's a way to do it, but I have not figured out a good, clean way to do it yet without having to do a whole bunch of manual math on it before I put it into the distribution. I will figure it out, but I have not figured it out up to this point. So I can just speak about it here, but I can show you something similar here, which is the next thing I wanted to show, which is cumulative probability distributions. So this is a nice visual showing both a regular probability, normally distributed probability view, and then that same distribution, except it's been made cumulative. And all that it does when you change it from the normal distribution to the cumulative one is it just adds it up as it goes. So it starts essentially, well, it starts the same as what it would for your normal distribution, and as it works across, it just adds up. So as you work your way across, this is going to keep getting taller until at this point, 100% of the data points fall here or less. So it's always at 1. That's how the cumulative one works. It's just another view of the same thing. You can do that. You saw me, I had that checkbox there. I can just share that again. I'm going to take off the split by. And so this is just looking at diameter. Again, that same stuff we were looking at before. But if I check this box that says show cumulative distribution, fortunately, it's not normalized to 0 to 1, which annoys me. But you can see that as I work my way to the right, each of the bins, it's the previous bin added to it. So by the time you get to the end, you've got, I'm sorry, this last bin is the addition of all of the data in the other bins. So I'm not saying that the way I want to. Especially once you're here, everything is equal to or less than. So you always end up with a curve that looks like this. Now, it's not always going to be identical to that. It depends on the distribution. It always will work its way up to 1 or 100%, or the total possible highest item in the data points range, or the data sets range on the right side. So everything is either, what does it look like? 2800 frequency. There's 2800 data points, so 2800 of them are here or less, but only 200 of them are here or less. So it just gives you an idea of where that range, where the data points that you're putting in fit in the range. Now, I think I'm just going to stick to it here because I like showing this part, because this is something I find to be pretty cool as far as showing probability. Let's see if I can get it to work the way I did earlier. So if I take and I split again, and I show probabilities, there was one that was really telling that I liked. Come on now, which one was it? Yeah, now it's going to speak me. it was in the iris data set that I was showing it. Let me show it in that one. Why is that not here? Nope, it wasn't. I apologize. I had this the way I wanted it, and now it's not showing. What I wanted to show was that when you do two of them together, it kind of makes almost what you could consider a simple model. And by just looking at this one thing, so if I look at length, the green bar is male, or the green distribution is male. The blue distribution is female. So if you were to have someone give you a length, there it is. That's what I wanted. I wanted to turn off cumulative. If somebody gave you a length of a abalone, and they said it was 2.2 inches, I assume that's in inches, maybe it's in millimeters, 0.2, I could tell you with fairly good certainty that it is a male. Because you can see male, if it's 0.2, it's much more probable for it to be male than female. If someone were to give me a length of 0.6, it's more likely, slightly more likely that it is a female as opposed to a male. It's just kind of interesting to be able to put these two probability curves on the same view. Height was another one that was really telling. If it's that's not what I wanted to tell you. If it's, let's say they counted rings and told me there was 29 rings, it's much more likely that it's female than male. So I could say there's an 80% probability just based on that one data point that it is female instead of male. So it's just kind of interesting. Obviously, you can make a model that does more than that, where you could have a bunch of points, but it's just a very quick way to do that if your visual will cooperate, which sometimes it does, sometimes it doesn't. So that's another thing you can do with distributions. You can split them and see how they stack against each other. I did get a good visual of it in Blackboard, so that one's in there, showing how to stack together. Let's see. Okay, so that was just showing probability distributions in orange. And then, okay, so that was everything for topic one, just a few new tools that you can use. Topic two is about subsetting the data, or another good term for it is dimensionality reduction, which sounds really fancy. But essentially, I've said essentially too much tonight. What dimensionality reduction is it is simplifying our analysis by figuring out which features we could remove because we find that they don't have much effect on the result. That's one way to do dimensionality reduction. There are multiple ways we can do this particular thing, and I'm going to demonstrate a few of them in orange. There's linear projection, principal component analysis, and feature ranking. And you can do all three of these at one level or another in orange, and I'll ask you to do this in the assignment. Use one or more of these to try to determine which features could be removed, or principal component analysis isn't actually a feature reduction, but it is a dimensionality reduction, which there is a difference. Feature reduction is finding things that we don't need, whereas principal component analysis is a way to simplify the crunching for processing. But again, I'll show you. So let's start with linear projection. So now I'm gonna go down into the iris data set because this one works well for some of the stuff that we're doing here. Because it's only got a few features, it's easier to see. So again, iris data set, and then I am utilizing an object called linear projection. And when I launch this, it's going to go on the wrong screen. And what linear projection does, if you were to think about it in three-dimensional space, which is the best we can do because we can't look at things in eight-dimensional space. If you looked at it in three-dimensional space, imagine it's a cube. A linear projection, you could think of it as looking at the cube directly from one side. And so you are taking a three-dimensional object in that case and reducing it down to 2 dimensions. And by doing that, you can decrease the number of, you can see which angle, I guess, of the cube gives you the best splitting of the data. And so you could determine which features are the most necessary for your analysis, because you can see in two-dimensional space or in lower dimensional space how they split the data instead of trying to look at it in crazy many dimensions. So here, this one only has 4 dimensions, so it's not too bad. One thing that's nice, again, it's a nice cheat here. You can hit suggest features, and it will tell you which ones it thinks makes the most sense to visualize it. So it actually likes all of them in this case. But I can put in or remove. Is it going to let me make this any bigger? Nope. There we go. I can put into my projection or remove any of them that I want. You can see the ones that are above this line are in the projection right now, and the ones that are not are below. So if I add that in, now I'm trying to look at this in 4 dimensions, which is not super useful. But I can take out one, and I can see, well, this one, if I have sepal width, length, and or sepal width, petal length, and petal width, I get a really good break on blue, which is setosa. But if I take that out, and I can take this down to, let's say, these 3, that one has a bit of a jumble around red and green. Blue, again, is still stands out well. This is kind of a guess and check thing to see which ones make the most sense. It looks like in a lot of these, in this case, blue just stands out in every case. That one seems to be a pretty decent 2-dimensional, where I've got sepal length and petal width. You know, I've got my green, my red, and my blue. If I add sepal width, that doesn't seem to make a lot of change. If I add petal length, that doesn't seem to make a ton of change either. So what I'm doing here is I'm just trying to look at this to find which features give me the best grouping. And again, utilizing something like suggest features here lets me, if I had 25 different dimensions, it could help me figure out which ones appear to be the best for splitting, so I can look at them. With 4, I could just kind of click through them, and I can visualize differently, you know, if I wanted to change the color based on the sepal length. In this case, it really only makes sense to do it on my category. And these are useful if you've got a lot of different data points that you want to try to view differently, just like we've done with stuff. I can also adjust things like symbol size stuff. That's all just general stuff. The point here is taking a higher dimensional space and trying to reduce it down and see which components or which features or which attributes, whichever term you want to use, have the most effect on distribution of the groupings. And if I find, let's say I like sepal length, petal width, and petal length, I can leave it like this. And then at the output of my projection, those are the ones that will get passed. If I use selected data to my table, so I should be able to do that. Huh. Okay, that seems like that's a weird thing. I should be able to, because I have selected them. I'm not sure why that's not acting like it should. It should pass me the selected data. I don't know why it's being goofy. gives me a column called select. It says no for everything. That's not working right, so I apologize. But I guess you can utilize linear projection to try to figure out, but passing it along, I have to hit up the community on that, see why that's not working. Does anybody see a select option that I'm missing? I don't. Huh. Yeah. Well, anyway, sorry about that. But that's linear projection. So that's one way you can try to reduce features, is by just visually looking at them in different combinations to figure out which ones create the best differentiation between the data points. Kind of and check a little bit. It's not super, but it is there. And the advantage that we're trying to get to here by doing these reductions would not be important for something like the iris data set. It would be something where you have 70 features and 35 million rows of data that you're trying to crunch. In that case, your processing power is starting to have a significant effect, or the amount of time that you have to process, or let's say a real-time type analysis is getting too high. You're crunching too long, you're spending too much, you're not getting to your results fast enough. In those cases, dimension reductionality is important. This is one way to try to determine which features are important. Another way is principal component analysis. So like I said, this is not one where you attempt to reduce features. This is one where you can, there's no easy way to explain this, but it essentially takes your data and converts it into eigenvectors. And with that, you can determine which principal components, after having been converted to eigenfactors, have the most effect on the output. And you can then utilize that information to create your models. So in a way, you have less features. Those features that you have are actually a combination of all your existing features. So you get the advantage of having all of your features. However, you have a lower processing overhead for it. I have not put a video out about it yet. I think I need to find a good video about it, because I don't think you can avoid math on it entirely and actually understand it. But you can see here, again, with a nice visual, when I put a PCA object on this, what I'm looking to do here is I'm looking to get a certain amount of the variance determined by the least number of components. And the amount of variance that's acceptable really depends on the modeling that you're doing. A rule of thumb is that if you can explain 80% of the variance, that's acceptable. Now for this iris data set, and the variance visually here is determined by how far this line is away from this line. You can see 9.995, 99.5% of the variance is explained with just 3 principal components here. If you have more, these things go out further. I think I put one of these on here too. Here, this one again, it splits fairly quickly, but at about, well, this one again, you could get away with just 2 principal components. These are just great data sets apparently, but you can figure out how much of the variance you want to, you need to have explained by the principal components, and then that is all that you would pass through to the model. And the way this works is it has, again, turned all of your data attributes into eigenvectors, and then it has figured out which ones are best at explaining the data. And so principal component 1 is the one that it has determined is the highest value in explaining the data. The principal component 2 is the second highest, 3, 4. So it has sorted these principal components that it's created from the most effect to the least effect, and then you have to determine how many of them that you want when you actually create your model. So if I wanted 5 of them, let's say, I just leave that on 5, and then I can break my program. There we go. There's 3 possible outputs to this thing. I can look at the components, I can look at the transformed data, or I can you can pass the transform data to k-means in this case. But if I look at components, you can see that it shows me those 5 principal components. I can't tell anymore what attribute contributed to those principal components. All I have is the principal component. So you kind of lose that view into which data point actually is affecting your data the most, because it has become these components. You can see that each one of these, so the sex is affected the most by principal component 2. So it is 0.66. The closer it is to 1 means that that component has the most effect on that attribute. Negative would be the inverse, obviously. Infant is the most affected by principal component 3. Male is the most affected by very little, in fact, but principal component 1. Length is most explained by principal component 1. So you can see that the higher that number is, the more it's explained, or the variance is explained by those principal components. I think this is probably the most weird thing I've had to explain to you this semester. So if it doesn't make sense right off, that's fine. I think along with that announcement where I'm going to figure out why the plus or minus is there, I'll throw a video in that I think will explain this in a clear manner without getting too crazy on the math, so you can understand it. But the goal here is, I mean, this data set has, I don't know, 11 features or something. I have taken the highest value stuff, converted it into these components, and now when I actually go to run my model, I only have 5 features that have to run through the model. And now I have a model that can run faster with less processing overhead. That's really the point of principal component. So I stuck a k-means off at the end of this just to show it working, but it's anything special. But I could then feed that transform data into a model and work with it. Okay, the third one is a little bit easier to understand. It's one I like the best, is ranking. So you can see I've got a rank object here, and I've just attached it to my data set. And I can open this up and get it over to the right window. And this one speaks in the language of info gain and gain ratio. And you can see that it's very quickly easy to see that petal length, petal width are the most useful attributes in this data set. They have the highest info gain, which means they're contributing the most to determining which type of iris it is. And sepal width is kind of useless. And even sepal length is I guess questionable in comparison to the other two. So I could very quickly look at this and go, I could dump sepal width and not miss it in my data analysis because it doesn't really give me any value. So that's a very quick way to trim the low value attributes out of your data set. And this is actually removing the attributes themselves. This isn't like principal component. This is, you would say, I don't want, you can select them here. And this one I know works. I don't know why that other one wasn't working, but I can select the ones that I want, and then I can attach something to the output of my ranking. I do this k-means again, and just pass it on through the model process. That's ranking. I showed it to you last. Maybe I should have showed it to you first because it's the easiest one to understand. But you can just attach it to your data set and figure out which attribute. If your data set has a target on it, you got to have a target variable for it to work against. Which components are best at explaining that target variable or getting you to that target variable. And then I think I just had my last slide is pretty straightforward. Just can't remember what it was I was going to share from it. Okay, correlations. So I just wanted to show you how correlations work in Orange. What you can do with correlations is essentially are comparing two data attributes in your data set to see how they are related, how much of a correlation there are between the two data points. It's kind of a good thing to know to see how they are related. If you have something, if you have two data points that are very highly correlated, Maybe you don't need them both. Maybe there's no point in having them in there independently. You could dump one, but it's also just nice to know how one affects another. And the way this works is you could look at it as doing kind of a linear regression on each one of your data points together. So you can take two data points and see how one explains the other, whether they're directly coordinated or directly correlated or inversely correlated. So I'm gonna just go back over to my data here one last time. And again, this is just a simple, I just attach a correlations object on the output of my data set. Again, get it over to the right screen. I don't know exactly how it comes in by default. In this case, I've got it set to all combinations, which will just directly compare all of the different data attributes to figure out how they correlate. And very quickly, you can see petal length, petal width are very, very highly correlated. 1 is a perfect correlation, and this is 0.963, which is very high. Petal length, sepal length, pretty high too. Petal width, sepal length, somewhat high, and then the rest of them are actually inversely correlated. So the longer the petal length, the lower the sepal width. Is how you could consider that. So if it was a linear regression, if you were visualizing a linear regression, it would start at the top left and work its way to the bottom right. So as petal length gets longer, sepal width gets shorter or less. So it would go from upper left to lower right, whereas directly coordinated would go from lower left to upper right. You can choose your combinations if you didn't want to look at them all. You pick one data point or one data attribute and compare it to everything else. Because like this one's really easy because there's so little data, but when you get into this one, if you try to do all combinations, it gets to be kind of a long list. So you can say, well, I'm kind of curious how diameter is compared to everything else. And I can see that this data set, a lot of things are highly coordinated, correlated, which makes sense because as they abalone gets larger, presumably it gets longer, it gets heavier, it has more rings. I mean, it feels like that's probably fairly obvious because they get bigger and in scale, not they don't get longer and then shorter. That doesn't make a lot of sense. So I would expect a lot of correlation between the data points in here, which tells me that if I was trying to create a model off this, I could dump a lot of these attributes without necessarily affecting the model, depending on what I'm trying to do. So that's correlation. You'll want to do that. Again, these are all quick things that you can do when you're trying to do this exploratory analysis on your data. When you find weird things, those are the places that you need to dig in a little bit, or you can figure out which data points aren't worth your effort. You could dump a few of them. Things of that nature to try to prep yourself for that all-important modeling process, because you are truly ready at that point. You understand what you're doing with your data, what your data looks like, what your data means, and then you're ready to actually start. It seems like it should be near the beginning of the process, but is often near the end because you've done all the preparation work. That is what I wanted to show you tonight. Any questions on all that? Okay, well, I've opened up the Blackboard module. I did it just before class. Probably should have done a little bit earlier, but that's out there. Similar to what I've shared here as far as the examples, but I've tried to put in just information so you can understand what these different things mean, and nice visuals to try to make things a little bit easier. I'm willing to share this program if you want, but I don't think you really need me to. You can throw these things together pretty quickly. If somebody wants it, I'll be glad to put it out there. I have found that moving around these orange projects is not working well, unfortunately. It seems like when you transfer them from one person to another, certain components don't like to be transferred. I still need to figure out why that is. I don't know if there's some kind of supporting file or something that is being missed when we try to move the OWS files around. But I need to dig on that a little bit more. However, I'm willing to try to send this to somebody interested or try to put it on Blackboard, but I just don't know how it's going to look when you download it. Okay, and any questions, comments, anything? Otherwise, I'm here. You guys can work, stick around, bounce if you like, and just hit me up later if you have questions, whatever you want. Again, there's just one assignment where I'm asking you to utilize a data set. You can utilize one of the pre-built ones in orange if you like, or you can just go grab another one from wherever or something that you're interested in. I think it's cool when people dig into data sets that are in topic matter that they're interested in, but I understand if you just want to work with what's already there. Don't have a problem with that. If you do work with your own data set, please make sure that you submit the data set with your analysis. So I have